One method of finding the general solution of a non-homogeneous differential equation is through method of undetermined coefficients. Learn more about it here in Engineering Math 5. How do we compare the structure of a non-homogeneous differential equation? As we discussed in the previous video, the structure of a homogeneous differential equation would have the derivatives equated with 0. A non-homogeneous differential equation, on the contrary, would have the derivatives equated to a function of x or the independent variable. The solution for non-homogeneous differential equation is given by y, which is equal to yc plus yp. Yc is term from complementary function. This term focuses on the left side of the equation or the expression with derivatives, and it considers it as a homogeneous equation. Yp, on the other hand, is also known as particular solution, and it works on the right side of the equation where the function of x is located. In this video, Yp will be computed using method of undetermined coefficients. What is the method of undetermined coefficients? It is a partial solution for non-homogeneous differential equations where pattern is formatted from the structure of the function of x. There are some restrictions though. MUC is limited when f of x is exponential, polynomial, or with sine or cosine and their combinations. For exponential structure, the pattern used is capital A times e raised to x, where we look for a. In first-degree polynomial structures, we use ax plus b, and quadratic equations will require ax squared plus bx plus c. For those with sine and cosine structures, yp is computed as a cosine of x plus b times sine of x. There are also combinations where the yp patterns will also just be combined. Moving on to the first example to show how the procedure works with y double prime minus 4y prime less 5y is equal to 14 less 30x. Our general solution y is computed as yc plus yp. And yc will follow the procedure of homogeneous differential equation, so we make y double prime minus 4y prime less 5y equal to 0. Just the same, we get the auxiliary equation from the derivatives and then factor it to find the roots, so we have m minus 5 times the quantity of m plus 1 is equal to 0, giving m1 as 5 and m2 as negative 1. We got distinct roots, so yc will be with case 1 pattern, which is c1 times e raised to 5x plus c2 times e raised to negative x. For yp, focus on the structure of fx, which is 14 minus 30x, a polynomial, so the pattern of yp is ax plus b. Take the derivative according to the degree of the differential equation. In this example, we have y double prime, which requires us to take the second derivative of yp. So y prime of p is just from ax, which is a, and as b is constant, we are going to have it as 0. And then the second derivative of yp is just 0. With yp and the derivatives already known, we can plug them into the original equation, so y double prime is 0, followed by negative 4y prime, which becomes negative 4a, then minus 5y, which is then 5 times the quantity of ax plus b. Then they are equated to 14 less 30x. Expand the terms to identify which terms go together. Then separately solve for a and b. Starting with terms with x, we have negative 5ax is equal to negative 30x, giving us a as 6. With a group of constants, negative 4a plus 5b is equal to 14. Plug a as 6, leaving b as the only unknown, and it is computed as negative 38 all over 5. Learning a as 6 and b as negative 38 all over 5, we can complete yp as 6x less 38 all over 5. Then finally, yc and yp can be combined for the general solution of the DE, and that is y is equal to c1 times e raised to 5x plus c2 times e raised to negative x plus 6x minus 38 all over 5. The second example requires the general solution of the differential equation y double prime plus y prime less 2y is equal to 2x minus 40 times cosine of 2x. Start with yc by taking the auxiliary equation, which is m squared plus m minus 2 is equal to 0. And this is factorable, giving the roots 1 and negative 2. So we have distinct roots. Thus, from the standard format, using distinct roots, we get yc as c1 times e raised to x plus c2 times e raised to negative 2x. Then yp considers 2x minus 40 times cosine of 2x. 2x is a polynomial which would require ax plus b. And then it is combined with negative 40 cosine of 2x, which is trigonometric. Asking for the pattern, c times cosine 2x plus d times sine of 2x. Combine all the terms to form yp. Now yp would need to be differentiated twice as the original DE requires. So yp prime is a minus 2c times sine of 2x plus 2d times cosine of 2x. And yp double prime becomes negative 4 times c cosine of 2x minus 4 times d times sine of 2x. Then associate yp to the derivatives in the equation, so we get the long equation when the groupings follow. Expand those with multipliers and then collect terms to be compared with the right function. Let's start with terms having cosine. We have negative 4c times cosine of 2x plus 2d times cosine of 2x minus 2c times cosine of 2x, and this is equated to negative 40 times cosine of 2x. By canceling out cosine 2x, we are left with negative 6c plus 2d is equal to negative 40. And this is our first equation. Now focus on terms with sign. So we have negative 4d times sine of 2x minus 2c times sine of 2x minus 2d times sine of 2x, and this is equated to 0, which we can take as 0 times sine of 2x. And factoring out sine of 2x again, we get negative 60 minus 2c is equal to 0. This is our second equation. Now take the terms with variable x. There is only negative 2 times ax, which is equated to 2x, thus a is computed as negative 1. Take this as the third equation. And lastly, the terms with pure constants, and we have a minus 2b, and this is equated to 0. This is the fourth equation. So what we have is a system of linear equations where we can readily compute the unknown coefficients. If we start by replacing a as negative 1 to equation 4, we can determine b, which is taken as negative 1/2. For c and d, we can work with the first and second equations, where we multiply the third equation by 3, resulting to negative 18c plus 60 is equal to negative 120. This will be added to the second equation, where 6t cancels out with negative 6t, and we get negative 20c is equal to negative 120. So c is determined as positive 6. Substituting c back into the second equation, we get d would be equal to negative 2. Now, having all the values of the unknown coefficients, we simply plug them into yp. Then finally, we complete y, which is yc plus yp, with c1 times e raised to x plus c2 times e raised to negative 2x minus x minus 1/2 plus 6 cosine 2x minus 2 sine of 2x. At this point, each term in the equation is distinct, so we take this as the general solution.